In this question, we are given that the half-life of a radioactive substance is 20 years and only 8 milligram remains after 100 years. And in this situation, we have to determine the initial amount of the radioactive substance. So first, I'm going to write down the equation which represents the amount of the substance at time t. So we can write down this as AF equals A0 e raised to the power of negative kT, where this AF represents the amount, that is the final amount of the radioactive substance. This is the final amount, or we can say this amount after t years. Amount after time t. And this A naught is the initial or the original amount. And K is the growth or the decay rate. Here, since we have a negative, it is we can consider this as a decay rate, because since we are dealing with a half-life problem, the radioactive substance is going to decay for every 20 years. So we write down this model as e raised to the power of negative of kT. So t is the time, and here the time is in years. And we will also use the formula for k. This is equal to natural logarithm of 2 over t half. This t half represents the half-life of the radioactive substance. Half-life of the radioactive substance. So this formula is already proved for half-life kind of problems. So we can use this when we have to solve any half-life problems. So that is k equals natural logarithm of t 2 over t half. And let's determine the value of k, because the half-life is given as 20 years. That means t half, this equals 20 years. We can substitute in this formula for k. So we get k equals natural logarithm over t half is 20. So this is the value of k that we have determined. Now I'm going to substitute this value of k into the model, that is for which represents the amount after time t. So therefore the model will become AF, which is the final amount, and this equals A naught e raised to the power of negative k times t, that is k is a natural logarithm of 2 over 20 times of t. So we are going to place this model to find the initial amount. Now let's use the other information, that is after 100 years, it is found to be that only 8 milligram of the radioactive substance is present. So if we convert that to mathematical, we see that when t equal to 100, the AF, which is the final amount of the radioactive substance, is only 8 milligrams. Let's substitute this into this model. So therefore, AF equal to 8 milligram. I put this 8 without the units, and this equals A naught e raised to the power of negative natural logarithm of 2 divided by 20 times t equals 100. So we replace t by 100. Now we can do some simplification. That is, we cancel this 100 by 20. This goes 5 times. And this means we can simplify and rewrite this equation as 8 equals A naught e raised to the power of, this is 5. 5 times of uh, natural logarithm of 2, but we have negative. So we can write this as negative 5 natural logarithm of 2. Let's continue. I'm going to rewrite this expression. That is, we have negative 5 natural logarithm of 2 using the power rule of logarithm. This negative 5 can be raised to the power of 2. So therefore, it is natural logarithm of 2 raised to the power of negative 5. I'm going to read it like this. So this implies 8 equals A naught e raised to the power of natural logarithm of 2 raised to the power of negative 5. So now we know that this exponential function and the natural logarithm function are inverse to each other. So they cancel out each other and giving, we have 8 here. This equals a naught times of 2 power negative 5. Now we can determine a naught from this equation. So let's continue simplifying. This 8 equals, we have a naught 2 raised to the power of negative 5. We can write down this as divided by 2 raised to the power of positive 5. So this gives the value of a. This is a naught equal 2 power 5 times of 8. We just multiply both sides by 2 power 5 to get a naught. So therefore a naught, and this equals 2 power 5 is 32. So 32 times of 8, and this equals 256. So we get a naught equals 256, and this should be in grams. So therefore the initial amount of the radioactive substances represented by a naught, and this equals 256 grams. This is the initial amount of the radioactive substance.